Hello, welcome back to CSC 263 Database Management Systems at Adelphi University. In the previous video we started talking about database internals, and specifically we talked about transactions and transaction properties, which could be summarized as ACID: atomicity, consistency, isolation, and durability. What we explained also is that we need these transactions to support concurrency. However, with transactions and concurrency comes a problem for example, the lost update problem. We introduced the concept of locks and locking to solve that problem, but also to introduce a new problem called deadlocks, and then we talked about how to solve deadlocks. In this video we'll talk about indexes and particularly what role indexing plays in the database management system. So first of all, it's important to realize that indexing is in many ways an optimization technique. It's a technique we use to make the database respond faster when we are looking for data in the database. And that makes sense because we have this principle that data is in principle unsorted in the database itself. The database is a set, and a set has no ordering. And that basically means that if we are searching for a particular record or a group of records or tuples, we basically have to go from the beginning till the end through the database and test each of our tuples against whatever criteria that we are looking for to determine whether or not they are part of our output set. And that is inefficient, especially when we have a large database. It's something that we want to avoid as much as we can. However, if our database is relatively small and there is no need to optimize, by all means don't go about creating indexes if you don't need them. Your DBMS might create some indexes in the background for you, but that's their business. That doesn't necessarily affect the complexity of your schedule, your schema. Keep in mind though that indexing is an optimization technique, and that could be a very valuable one, but it's not one that you always need. Now, indexing as an optimization technique is one application, but the other application in some ways is to enforce constraints. And this is what Postgres does. In Postgres, if we define a primary key, we're actually defining an index with some constraints on the index rather than on the database directly. And at that point it's no longer an option, you kind of have to do this. But again, the DBMS will take care of that for you. Now, having said that, if you know that you're going to create a database that is heavily queried on specific fields, criteria involving particular columns, then consider creating an index on those columns to speed up those searches. Again, you don't always have to do it. It is an optimization technique, and optimization is optional in most cases. But it could be useful. Creating an index is a database-specific action, so there is no universal technique for doing that. But one way we could do that, which is similar in most databases, would be just using the create index statement. You probably want to create at least a meaningful name. In this case I did PK students index, which means that I am creating an index on the primary key of students, and I'm doing that on the student ID field ascending. If I know that I'm going to search my database that way, that's a good way of doing it. You don't have to maintain an index. The index is maintained by the database management system. What we do know is that from our computer science knowledge, especially when we talk about searchable data structures, we often deal with trees, and that these are computer science trees. And so a binary search, we've talked about that one in the past, is a very efficient way of searching. Remember, the binary search assumes that you have a sorted list of data and that you can just chop the data in half and say, well, at that halfway point, is that the data I'm looking for? If the answer is no, then you're going to look and see if that halfway point data is greater than or less than the data that you're looking for. So you know you need to look to the left or to the right of that halfway point. And then you repeat the process. So basically each time you're chopping your search space in half. And that leads to very efficient searches. It's tree-based though. So the basic terminology of a tree is that a tree consists of nodes. The nodes are organized in a hierarchy, where the root node is the topmost node. And then below the topmost node, we have children. Like every other node could have children below it. If a node has a parent, and a node has at least one child, at that point we call it an internal node. If a node has no children, only a parent, at that point we call it a leaf node. And so the number of layers I can distinguish in my tree is the height of the tree. And for a search perspective, in many cases you want to keep the height fairly limited so that we can descend our tree pretty fast. So let's take a look at binary trees in this case. Now let's say that I have this collection of values. There's a bunch of numbers there. 1, 2, 5, 6, 7, 9, 12, all the way up to 33. Now keep in mind two things. One, it's numbers, and numbers can be sorted. If I don't have a value that is sortable, in other words, it's not an ordinal value, then it's going to be not possible to use the binary tree like this. So we're going to assume that whatever values we're looking for are ordinal values. And two, I'm starting at this point from a sorted list of values. And that's an important one, because if I would start with an unsorted list of values, this wouldn't work as well. So how do I do this? How do I build this search tree? Let's first see if we can use it. So for example, I am looking for the value 21. Is that part of my database? In other words, is there a node that is indexed by the value 21? If I look at my list of values, I have to first start at 1 and say, well, 1 is not 21. So I go to 2 and to 5 to 6 to 7, all the way down to 21. And that means that I have taken 11 steps through my list before I found that the value I'm looking for is in fact part of this list of values, and I can retrieve it. If I hit the end of my list without finding it, I would have known it wasn't part of the list. But all in all, this is not a very efficient way. If I use this tree that I have here, I would start at the value 9, and I say, well, I'm looking for 21. 9 is less than 21. In other words, 21 is more than 9. I'm going to go down the right-hand side of this binary tree. And now I'm at 18, and I'm going to make that comparison again. I'm looking for 21, but 21 is more than 18. And I'm going to go down the right side of 18 again, and now I found 21. So this is really only 3 steps, the root, 18, and 21. And in 3 steps I found my value, rather than in the 11 steps that I found it before, which of course is much faster. And I can do this by eliminating whole areas of my search space each time that I make this comparison. If I start at the top again at 9, and I determine that 21 is more than 9, I eliminate the search space that includes all the values less than 9. At 18, I do the same thing again. If I determine that 21 is more than 18, I eliminate all the values that are between 9 and 18. And so I make my search space smaller and smaller each time. Now in this case, I put this tree together by looking at my sorted list and go sit in the middle. These are, 12 values, so I picked the middle one, which was 9. And then I said, okay, let's split whatever we have left of 9, again in half. That was the 5 point. And then, I did it each time. So I constructed this tree specifically for this sorted list. Now, if I would have to add a value to this tree, there's a good chance I may have to reorder this list in order to retain its maximum efficiency. And that's where we start looking at a problem with indexes. Indexes need to be maintained. And that means that every time that I insert new data, I remove data, or I make changes to data, my tree, or my index I should say, has to be regenerated, or at least has to be updated. And that means that creating indexes adds overhead. Overhead each time that you manipulate the data by changing it, creating it, or deleting it. So what we're looking for is not only a way that speeds up our search, but we're also looking for a mechanism that the overhead associated with changing data is minimal. And so the binary tree has these issues. I mentioned this, every time an index is added, removed, or updated, it must be regenerated or updated. The other part is that from a practical perspective, the binary tree is not a very efficient tree. Mathematically it is, but we have to remember that when we are dealing with computers, we also have to keep in mind the physical realm. And the way that a computer works, especially when it retrieves data from disk or from any secondary storage, it reads a block of data at a time, not just one value. A block of data could be as large as 4 kilobytes, and that means that a block of data can never be less than 4 kilobytes. And that means that if I'm going to take my index, and each of my index values is going to be in a block, I have to go back and forth to different blocks very often. What I want to do is map my blocks to my index, so that I can load as much data as I can when I go to disk and use that in a meaningful way. A variation of the binary tree that is very much more efficient in dealing with blocks of data on a disk is called the B tree. And so the B tree is a data structure that has a couple of changes compared to the binary tree. Each node can have multiple values, not just one. And each node can have multiple children, not just 2, like in the binary node. And by doing those changes and adding some rules to this, I create a more efficient algorithm. And let's take a look at that algorithm. The B tree is a self-balancing tree, which means that as I add removed values to my tree, the tree itself restructures in order to retain its efficiency. It can search in logarithmic time, which is really good. That means that the maximum number of searches is the logarithm of the size of the database. So we saw that same thing with the binary tree. It's the same mechanism. The B tree, though, is different than the binary tree, and so the names are a little confusing, but the B tree has an order associated with it. The order is the maximum number of children that the node can have. What we know is that each node may contain at least the number order, so that's m, minus 1 values. So if I have a tree of order 5, each node can only contain 4 values, but it can have 5 children. There's also a minimum of the number of values that we have. M over 2 minus 1. So 2.5, and 3 of order 5 divided by 2 is 2.5. Minus 1 is 1.5. Now I can't have 1.5 values, so I need to have at least 2 values in there then. Which means that if I have a tree of order 5, each node has to have at least 2 values, and at most 4 values in it. Footnote, that's true for all nodes except the root. The root can have less values in it. And then within each node, the values are stored in an ascending order so we can more easily split it. If a node becomes full, we have to split it. Now, what does that mean in practice? Because this is very abstract, even though it's correct. It's a little bit like what? Let's take a look at an example. Now, I have a bunch of values. I have the values 1, 2, 34, 13, 21, 5, 3, and 8. So first off, when we were looking at the binary tree, we were looking at a sorted list of values in order to create our tree. Here, the list of values is unsorted. There's no clear ordering in here. We're going to deal with the B tree of degree 5. And that means that I can have at most 4 nodes in 4 values in each node. And so the first 4 values, adding that to my B tree is really easy. They just get added to the root node. 1, 2, 13, and 34. Why that ordering? Well, because the values, the keys, are listed in order. So even though I first add 2, then I first add 1, then I add 2, then I add 34, but by the time I come 13, I put it into the right place. Now, the next value on my list is 21. but I'm not allowed to put 21 into this tree because that would overflow this root node. And that means at that point it's time to split up the root node. The easiest way to think about that is by adding that next value, at least temporarily, to the node. So now I get 1, 2, 13, 21, 34. And I look for whichever one is in the middle. 1, 2, it's 2 values. The last two are 21 and 34. That's 2 values at the end. That means 13 sits in the middle. 13 gets pushed out and goes up and becomes the new root node. And that means that to the left of 13, I have all values less than 13, in this case 1 and 2. And to the right of 13, I have all values greater than 13, which is 21 and 34. And so my tree just split itself from one node to a root node and two leaf nodes underneath. And as I continue to add values to my tree, we can now add the values 5 and 3, no problems. 5 and 3 are both less than 13, so they get added to the leaf node that's to the left of 13. Notice that values always get added to the leaves, and then if something pushes up, that happens as a second stage. So now we get the left leaf node is 1, 2, 3, and 5. The right leaf node is still the same. But it means that if I'm looking for a value, I'm looking for my value 21, for example, I can go to my root and I can say, well, that's, 13. 21 is more than 13, I gotta go right. And I find my 21 value right there. Now let's add the value 8. 8 is also less than 13. And that means it would get added to the left node that already contains 1, 2, 3, and 5, which is 4 values, which is all I am allowed to have. I'm going to add 8 anyway. I'm going to do 1, 2, 3, 5, and 8. But at that point, the element at the middle of that list, that's not too big, also gets pushed up to my root. And so my new root becomes the values 3 and 13. If I would have any values less than 3, and I do, 1 and 2, those go to the child that is to the left of 3. If I have any values between 3 and 13, and I do, those are 5 and 8, they could go to the child that is connected in between 3 and 13. And do I have any values larger than 13? Well, I do. It's 21 and 34. Well, then they go to the child that's mounted to the right of 34. And you see that my tree rebalanced itself again. Instead of having the 3 nodes, it now has 4 nodes. Still only 2 layers. It would stay, the depth would continue to be 2 until the root node also gets full, in which case the root node would split and a new root node would get created. And so the B tree is this balancing root that is very efficient to search. And as we can pick the the order of the tree to match the size of our blocks is pretty efficient on disk as well. When we deal in class, we'll start doing some exercises by adding more values to this so you can get some hands-on experience. Now this is not a course on data structures, so at this point I'm not going to worry about removing data from a node or by moving things around. That we'll cover in the CSC 273 class, which is the data structures class. Now the reason that I chose B trees is because B trees are widely used for database indexes. And as a matter of fact, the Postgres database does that too. If we look at the definition for any of our tables that have primary keys defined, we'll actually see that the way that Postgres implements a primary key is by defining an index. And that index is a B tree index, by default at least, unless you make changes to that. And the primary key constraints with unique and not null are defined on the index, not necessarily on the table itself. And that, of course, is just an efficiency measure that happens in the DBMS as a DBMS internal, so that we don't have to worry about it in our programming code. Okay, so that's indexes. Indexes as a mechanism to speed up search, but at the cost of some overhead. which can be minimized by choosing efficient algorithms, in our case the B-tree algorithm that we looked at in a little bit more detail. In the next video we'll talk about recovery. How do we get that persistence from the database figured out?